Welcome back to the Routing Loop. I'm Matt Lewis. I'm a solution architect over here at AWS. We've got Jamie, who you all know, another solution architect at AWS. We're your hosts for the Routing Loop this week. We also have Imen, solution architect in our telco IBU over here at AWS, and we've got a super interesting topic today. So I'm really excited about this one. This is going to be finding network root causes in seconds with digital twins and agentic AI. So one of the more practical and exciting applications of agentic AI that I've seen in recent times. So this is going to be really good. But I guess, Imen, do you want to do a quick intro and just tell us a little bit about yourself, where you come from, what kind of stuff you work on?
Excellent. So this is my first time on Twitch. I'm super excited. Thank you for having me.
Awesome.
I'm principal AI/ML solution architect, working mainly on network and AI, and in the journey toward the autonomous network and how to make the network smarter with the introduction step by step of the AI/ML part. And today the topic, as you said, is about how to put in place a network digital twin for what if scenario, but mainly for the root cause analysis to get started, to show, to reduce from a different lot of hours time consuming to get the root cause isolated in terms of having it in second and minute for different operators. So that's what will be our topic today.
And rumor has it you have a demo for us.
Yes, we have a demo that is representing real data in real city with our customers. We have different realization in production. Others are ongoing now as we speak, and others are starting to understand, the data governance, etc. So different maturities, but basically this is one of the most hot topic today in the telco industry: the autonomous network journey, building the governance of the data, and what is a network digital twin as a graph for their different operation task.
So I know we've got some slides too. I don't want to steal your thunder, but this concept of a digital twin is super interesting to me. And so let's see if I explain it correctly, and you can kind of tell me what my understanding of it is correct or not. But basically, we're taking telemetry data and I guess topology data, configuration data of what a physical, logical, virtual deployment is, and then putting that in something. And then we have a representation of that to say, hey, we've got a full copy of what we have out in our infrastructure, and we can then do things with that. We can detect things. We can then plug agentic AI into that to do some really advanced stuff. Does that sound about right?
Exactly. This is exactly what is a digital twin. I will add just with real-time representation of the network. So it really reflects how the network is evolving. Your telemetry is evolving from second to minute, depending on the time frame of collection. And the topology, it's for like the current network, telco network, but it can be also the dependencies, the relationships between the node if you're talking about AWS infrastructure. So think of it as your mirror of what's reflecting what is happening in your network, and then you top it with different level of intelligence. Agentic AI is one of them, but it can be also graph deep learning for completing the topology where you have missing links, missing network interfaces that the model can infer for you. Or you can have, for example, forecasting while taking into account the network node dependencies, distance, and, for example, the liter, the bandwidth, the jitter, the bandwidth, and the utilization in between different nodes. All of this can be taken into account, and the model can be trained on those dependencies plus all the evolution over time of the metric. So that's what.
Okay. So I think if anyone ever asked me about career progression and how to get ahead and what lessons have you learned in your career, mine is generally find your Venn diagram of success, where you're really deep in one area, you get a specialty in another area, and the Venn diagram of those two things is where unique and special things happen. And from what I'm hearing, I think your Venn diagram is really, you've got telecommunications on one side and then artificial intelligence on the other side. And so what we're presenting today really sits in between the two of those. Is that a fair statement?
It's a multidisciplinary domain where you need to understand the network so that you can frame it properly for the AI to get for you the insights. So that's how I got to these two words together. I see them always cognitive network as one word, but I understand it like definitely two words: the network and the AI. So that's.
And I think the people are always concerned that maybe an LLM will do their job for them. It really sounds like you're kind of coming at this from a different angle, where you're saying, hey, because of the specialties that I've worked on, or the areas that I've worked on, such as something like an LLM or an agent to get better outcomes. And so in that case, it's really just a tool like Excel, in my opinion, right? It's the next evolution of that.
Yeah. So it is definitely accelerator to get the insights right. But the LLM, I mean, there is no magic. You need to start by your raw data from the network, then you do the proper transformation, the proper preparation of the data, and then also the proper modeling of the data. That's why here the graph is very important. So when you capture the dependency as a graph data, when you capture telemetry as time series data, your alarms as tabular data, each data will fit the right format for it. And then the LLM will make the magic because you already prepared the data governance, the data preparation, all the transformation things. And you use the LLM for the problem that are for the LLM. And if you have like just anomaly detection or just forecasting, just use the regular AI for that. So it's the right technology for the right problem. That's the framing part that in any AI domain, you will start by problem framing, which means I understand my data, I frame the problem, then I will select which model I will use or which techniques I will use. That's
okay.
how.
Very cool. Well, should we get into some slides? Oh, go ahead, Jamie. Yeah.
I just have one quick question. You mentioned that you basically have to understand the data. Do you have any advice for anyone who is going to start a journey like this? Like, how do you know what's the right data?
Yeah, so basically you need some subject matter expertise on the network, but in the telco domain, we have a lot of standardization body like 3GPP, GSMA, and others. So there you will have the description of the data. You will have the network architecture, and then you will have the network node description, and then from each network node, you will know what type of, for example, key performance indicator you are collecting. You are understanding which alarm this node can emit, how these are related, and which network interface in between. So a lot of material there. And you can also use the LLM to understand, first of all, step by step, for example, mobile network, radio access network, which data I'm collecting, the explanation of the data catalog, and then step by step you go there. So for telco world, a lot of documentation exists on the data description for sure.
Okay. And then does the data, because it is a LLM, does it need to be human readable, or is it fine just to have just the raw metricing data? Because, we've had plenty of AI type folk on here, and a lot of them are always telling us the benefits of AI is the human readable answers, as well as that AI can go over, human readable text. So some of our logs, like from, VPC flow logs and other things, and edge logs, may not necessarily be human readable. So do you have any guidance or advice there?
So similar to the VPC data, also the telco data, it's not textual data. Those data are produced by machines, by routers, by VPC in the AWS infrastructure, by databases, by base stations. So those are produced by machines, so that they can the counter, for example, it can be like 50K columns of counters. So to make sense of it, it's not for a human. It is meant to be analyzed by a process, automated process. So basically, you go, first of all, you have to prepare the data in a way to be, for example, the volume of alarm, the volume of counters, clustering through some AI ML. But then you have the Gen AI that will be extracting those insights and summarization to the NOC team, for example, the network operational team, to the support engineers, to help them. Instead of looking to millions of logs, it will say, okay, you have 7 families of logs now that are appearing in this time frame, and this is what the problem I am seeing happening. So yeah, the LLM will make sense, but you need to prepare the data to some extent to benefit from that.
So the data is going to be the strong foundation that everything's sitting on top of.
Yes, we call this, the data is the fuel.
Okay, the fuel.
The fuel for everything is the data. And of course, you need to have the problem framing right so that you can have the LLM extracting for you the isolation of failure, the change that it might need to happen, or the scaling recommendation that you need to execute, these kind of things.
I'm going to steal that. The fuel. Data is the fuel.
Yeah. So let's start some slides, maybe. I will skip.
Yeah, that sounds good.
Introduction now.
Oh, sorry.
Yeah, we're good.
There we go.
Let me go to, so as I said, it's about the autonomous network journey. I will skip some slides here. We don't need everything. So autonomous network journey, think of it as network that it's self-healing, self-repairing, self-configuring, aware of the different metrics evolution, and this can be across the layer from the infrastructure to the apps, and also across the network segment, because you have the RAN, the core, the transport. You have different network segments, and you have different layers and different protocols that you need to take into account. So autonomous network journeys help to make this network self-configuring, self-repairing, etc. And this is the journey, because it's not like in one click. So the voice of the customer. So how we started, I mean, this is not like this is an old problem, how to make the operation always, cost effective and efficient, and help the NOC team to maintain their network as the customers expect them to happen in terms of quality of service. So basically, the most recurrent asks are about, I want to make sure that my network changes are mastered. There is no impact if I'm adding new node or new protocol or enabling new network interface, how I can master all those changes, how I can make sure that my end users are not impacted by those changes, so the service impact and the end user impact visibility, so that they can guarantee the quality of service. And the third one, which is where we're going to focus today, is the failure isolation. So this is across the different customers and partners I'm working with. Sometimes, from 7 hours plus 24 hours for very complex event to be detected. Because when it happens, you need to find in which layer, in which network node, and what was the problem. So it's like multi-dimensional type of data that you need to analyze. And it was always managed through threshold heuristics or rules, which are always becoming obsolete because the network is moving, the data is drifting, etc. And in the telco domain, it's also the network inventories where you are supposed to have what is active in your network today. So those are not accurate today. It's not up to date. So when you build your network for the first time, everything is there, but then it is not maintained over time, or at least not maintained to be used for real-time detection or real-time root cause analysis. And the last one, the dream for all the operators today, and the journey to that all the operators are following, is to have the closed loop. So I detect there is a problem. I have the recommendation. Now I want the activation. I want my network to go and self-configure itself because there is a problem that it's now known. Or also not even a problem. I want to scale. Detection of the need of scale, capacity adjustment, and the network will go and do it by itself. So this is the closed loop automation, continuous reconfiguration of the network part. So all exciting, and it's all become into AI for network and the data. Again, back to the data, give me the data and then put the transformation and then go from there.
So if I'm thinking about a traditional network environment, we would basically use SNMP or something to grab interface stats on a router and say, we know this is a 10 gig interface. We would take a per second poll of the usage and then graph that into something like MRTG. So now you've got an interface, we're slowly over time increasing over, weeks or months or whatever it may be, up until 10 gig, up until we get to say 4 gig, because it might be redundant, right? When we get to about 2 gig or 3 gig, we can then project and say, well, in about 2 months' time, we're going to reach this 40% utilization, and we don't want to have any capacity overruns in a failure. So we're going to then start to roll out new infrastructure. We're going to then start turning on more capacity or whatever it is. We would create a change implementation plan. Operations folks would go and implement the configuration. I'm talking physical equipment, so it's a little bit different here. But then that would be a 3 to 4 month process.
Yes, exactly. It's totally the point, Matt. So it's 3 months for any deployment, new reconfiguration or new updates on the network, and this is during the design. And then when it is up and running, then you have hours of diagnosis, of understanding what's the problem. And one of the most costly, at least percentage in the field engineering, is that the diagnosis and the root cause are not well prepared for the field engineer to go and perform the reparation, etc. So it's really.
I think that's why it's so such an interesting topic, because physical fiber deployment is still physical fiber deployment. You still need to do that stuff.
Yes.
But when your network starts growing, and then you have let's say a consumer calls into support and says, I'm getting poor performance. And then you look at your MRTG graphs of all your interfaces and you think, hold on a second, you're manually looking at that stuff and saying, well, is there a capacity overrun somewhere that traffic is going through a router where it's hitting 100% CPU, or an interface is oversubscribed and we missed it and we need to fix it? And that can take weeks as well. I've in my past life, I've literally mapped out layer 2 spanning tree networks manually by going in and saying, okay, let's look at every single interface and see what's online. Let's have a look at what interfaces are blocked. Let's have a look what the path would be, and sketching that out for about a week. And that's why I love creating diagrams, but it was because I was forced to do that for sanity, to say I need to create a diagram of the network now so I know exactly what's going on at this point in time. All that kind of goes out the window with this type of stuff. by the sounds of it.
Yeah.
Well, there's one other aspect to it too that I was thinking about. Back when you would make the networks and you're laying the fiber as you were talking about, you still have somewhat of a mental note of what router you plug what into. But once you get into the cloud, that's all abstracted from you. So like any of those clues that you would have had during the build, right, for when there's a problem, are not existent when you're doing this in the cloud, because again, all that stuff, I don't know which router was plugged into whatever or any type of thing under the hood, right? Because all we're seeing or all we get is the API or the console.
Yeah.
I think that's really the rise of ephemeral infrastructure which the cloud has enabled. I can still, back in my network engineering days, give you VTEP -E-005 is one of the switches that I used to work on. Right, I can visualize where I was standing in a data center, looking at a Catalyst 6500, looking at the ports and plugging in new fibers, because you have that physical context. I can't tell you what my instance IDs were yesterday or a year ago or 5 years ago.
And
right?
you can
Because
SNMP walk
ephemeral.
that, right? Get all the data out of it. You can go ahead and just do a write term and get all of the things that you've programmed into it and get more clues, which again, we don't have right now.
That's the scale also, it's also the scale of the network today. It's impossible. It's millions of instances, millions of routers, millions of, sites and cells and radio node if you take the telco network. And then from there you have, terabytes per day that needs to be analyzed. Like it is becoming no more that the human can just sit and do the diagrams. It's just impossible to do that, right? It's another dimension.
How many?
Yeah. Go ahead, Jim.
No, I was just going to say, how many times do you have like your Sun server that was running Cisco Works 2000 fill up all of its hard drives because you were logging something and forgot to turn it off?
Oops.
Oops.
So basically, it's what you were mentioning, Matt, about the definition. So the concept itself is, okay, I want to have my network smart enough and self-configuring, self-repairing, etc. So for that, I need to work out the knowledge. And a smart system or an autonomous system, it has to have a knowledge. And the knowledge, it's all about the data that needs to be represented in a way to extract the insights. So the digital twin is a digital representation, a real-time mirror of what's happening now on the network, and top it with 3 types of intelligence. So the graph analytics is one type of intelligence that will traverse your network topology, tell you which one is the most connected, which one is like, if it is failing, everything is down, or what are the similarity between the network node across the different regions. So those are ready graph analytics algorithm that we have in Amazon Neptune Analytics that can be leveraged directly. And the other one is about the deep learning zone graph, and here you will train your model to know your node dependencies. So like think of it like you have your VPC, your NAT gateway, your transit gateway, the EC2 instances, and this connection, you train a model to understand this. And then if there is any deviation, the model is spotting the deviation in the interfaces or new network topology, new network nodes it's added or instances. So it will learn from that the reference architecture, the reference topology, then it will detect whatever deviation happening. And of course, the agentic AI that will be consuming all this information. So it will go to your forecasting about whatever event happening in the network. It will access your topology as represented as a graph, and it will also be able to combine the prediction with the current states and then forecast what's happening in the future. So we will see some of this in the demo. So think of digital twin that can enable what-if scenarios. So with some customers in production, we have this for transmission network for service impact assessment. So they have a change, and then we can know what change will be impacting. And digital twin for root cause analysis is what we're going to talk about today. It was also on the blog with Docomo, our customer in Japan. I'm also working with a US customer where they have this for their cable network. So it is really across different type of networks. As far as we have dependencies, we can apply this. That's the logic of the digital twin.
Okay, let's keep rolling. Let's see what we got here.
Yeah. So clearly here, just easy representation, very high level. So this is how it looks like a network as a graph. So in my all the discussion I had with my customers and partners, I didn't need to explain why the network is a graph. Naturally, it is a graph. Everyone is convinced it is a graph. But it is a graph that is dynamic, moving over time. So basically here for the mobile network, you can have the base station, you have the users, you have they're connected into a cell, and then at every node you have information that you are collecting. So here you are having, we call this KPI, so key performance indicator. So you're collecting them at the cell level. It can be the drop call rate, it can be signal strength. So these are metrics that you are collecting at different nodes. And you can also have the alarms occurring at these different nodes. So your network, your network as a graph is a representation of the topology with all the telemetry that it's representing the temporal evolution of your network. So this is for mobile network. The same here, just to show that how it looks like if we are talking about our AWS infrastructure. So you have, as I said, the EC2 instances, you have the NAT gateway, transit gateway, and the VPC, and then you can measure also different metrics in between, and this also can be represented as a graph for the root cause analysis, for the failure isolation, and also for the changes that could happen across the different domains. So this is just to set the foundation, how the graph for the network looks like. Topology, dependencies, topped by alarms, KPIs, and any information that evolves over time. It can be configuration also that you want to represent. Now, the important part here is the temporal part and special temporal. So this is to say that your network will have changes from metrics perspective that you are collecting over time, but you can also have new nodes that you're adding, new instances EC2 that you are deploying, and you need this to be captured so that it is a real representation of reflecting what's happening in your network. So that's the other foundation part here. So it is a temporal dynamic graph that it's need to be maintained and built. So let's go to the basic, how we build this, what are the technology that we have now. Like 5 years ago, this couldn't happen. Okay, this is really now because the planets of the different technologies across the different domain are now aligned from the data perspective, from the AI perspective, and also from the maturity, the cloudification of the network that is ongoing. All these things are put together. We can now build this digital twin as a graph. So let me start by the bottom part. So it's about, again, the data is the fuel. So you get your data, the telemetry, for example, it can be in time stream DB. All the vectorization, for example, documentation about the catalog of the alarm, as Jamie was mentioning about, the data and description. So anything related to the description of the data, the cataloging, the alarm types. It can be in OpenSearch, it can be in S3 vector as embedding, so that the GenAI can make sense of it. And the network dependencies, topology, relationships, it will be in Amazon Neptune, the graph database in AWS. And all of this data, it's all connected together, because from the database and in the graph, you can know which node and which telemetry on the time stream DB and vice versa. The second layer here is about the intelligence. So the intelligence, it's not always LLM. It's not always deep learning. You must start by some statistics on your network. You need to understand the volume of your alarms, the pattern happening in your KPI. So this is the data discovery part, and some statistics are important. And here, so you can use just algorithm for graphs, for example, for the degree of the node, how many connections around that node. For example, clustering and understanding the community that you have and the different representation in your topology. And all of this can be with SageMaker, with Bedrock, with Amazon Neptune Analytics, and GraphStorm for the deep learning part. So this is like the full stack that you can cover at least 3-4 types of intelligence, from the stats to the classical AI ML, to the foundation models, and to the deep learning of graphs, which is actually a specific niche of deep learning in itself. And the top part of it is the agentic AI that will go and grab all the information from the prediction, from the databases, and make sense of it, and also actuate in the network if we're going to the closed loop to make this, for example, recovery happening. Okay, so I think we can now let's put them in motion now. These are the stack. Now let's have them all working together. So in all the customers I worked with, the first part is to build the topology or to build the model for the network. So this is this part can take months in the beginning if you are starting from raw data, but once it is done, it is becoming faster because the graph is meant to scale. You don't need to have a model to maintain, or the joint identifier between the different SQL database. You don't need that. It's node and edge, and they are connected together with other nodes. So once we build the topology as a graph, then we put it in Neptune. Then we can use graph deep learning to complement the topology. So this is graph neural network that we have in our Amazon Neptune ML, or through the GraphStorm, which is also an open source framework by AWS. And then you can use the type of model called link prediction that will be trained on your graph. understand your structure, and then point for you where you have missed some links or missed some nodes so that you can complement your topology. And the third step, you have your topology clean, it is stored and connected to all your telemetry. Now you have your digital twin and you can start the show. And the show will go through different intelligence. Now you have the graph analytics to find out the isolation of failure, understanding the graph statistics in the network, and you have the spatiotemporal forecasting, anomalies, and all the graph deep learning part in the step 5. And the agentic part on the bottom, accessing the topology, accessing the prediction analytics, and then grab the information. So I think it's the time to show this in the demo to make it more concrete. So if we can have the demo. So this demo here, so this is one of the demo we built. It was with Bedrock Agent, but now we are moving to Strand. I will show in the slides after the demo how we are putting it on Strand today. So this is basically...
But before we go, let's just pause the demo for a second. I just want to recap for everyone.
Yes, please.
So basically what we're doing here is we're taking... well, help me out here. We're taking a describe of an environment and saying basically a network is very akin to what a graph database model looks like, where you've got nodes and you've got connections. And so that's exactly what a network is. You've got basically nodes and then links between those fibers, between those nodes or routers or even instances or whatever it may be. You've got mechanisms that enable that connectivity, like potentially route tables or subnets or other things, which is fine. But once we get that topology into a graph database, we've then got a current view of the network. And then what you're saying is we're taking telemetry data from those entities out of the network to feed in real time into the same graph database, I'm assuming as well?
It will, in the same graph, you will have pointers to the telemetry. So for example, you will have KPI1, it is in the graph, but the values will be written in TimeStreamDB or Redshift or whatever. So here, your graph is having all the information, but the write will be in the right database. So you will write the telemetry in the right database, but you have the pointers in between. That's the...
So actions take place, right, from an understanding of the graph database.
Yes.
Changes are made. Those changes are written into the right database, like Redshift. And then once that's realized, that gets placed into the graph database. And then it fuels the AI even further.
The central part is your graph database. This represents for you how everything is connected. And in every node, you have what we call properties. So the properties is what Matt was mentioning, the telemetry part. And the telemetry part, you will have, I have like all my KPIs as a properties, but I will not write into Neptune every second or every 5 minutes. The values of those KPIs will be written into another database like TimeStreamDB or Redshift for the telemetry information. But the pointer from the graph to that, this is what we need as information to capture the telemetry.
How often would you say the graph database needs to be updated with topology information? Is there a cycle there that happens?
Yeah, so it depends on the customer. So some customers are updating this every 24 hours for the topology changes. For the temporal changes, they are writing directly into their tabular database or SQL databases or like TimeStreamDB database every 5 minutes, every 15 minutes. If it is probe data, it can be even at the second level. So it depends on the telemetry time frame of collection. But the topological part from 24 hours plus for the update of the topology, or 1 week, month, is it depend. Topology is very stable, I would say, in the telco world. Stable by means it's not every minute you are changing the node for now, but for the telemetry it is changing like all the time.
I think the reason why I ask is I understand the telemetry data, that's just a constant stream of data, and you need something that's able to handle that. But I wonder in AWS, environments are a little more dynamic than a physical network, right? It's not a month to deploy a new fiber. It's, hey, we have an event and I'm deploying 1,000 new nodes, EC2 instances or containers. So I wonder how that would apply. Anyway, so in summary, we've got the graph database that shows the topology. We've got the telemetry data stored somewhere with references in the graph database to that telemetry. And then what happens after that? What do we do with that?
So now we have everything there, and this is one of the examples. So this was presented with our customer Orange in the last reInvent, and let me play the demo. So this is happening in Pontevedra city in Spain, and here we can see this is like the portal where the NOC team will be accessing, and they will see their network topology there. So this is radio access network, transport network, and microwave devices. So it's across different domain and 3 vendors that are providing those network equipment. And here, for example, the NOC team is accessing the Nokia device. So you can see here that's a microwave device. Just by unfolding, it will find all the links that are connected to that microwave device. And just to mention that this looks very simple, but actually this is across 3 different domain, RAN, transport, and microwave, that they didn't have this end-to-end topology cross-network domain. That's for them already helpful for their day-to-day operation. And you can see that it includes, for example, here the base station. Those are, for example, the 4G and 5G base station, and then you have the microwave device connected and the routers on the other side. So this is first example of it is digital twin represented there. But now how I can use this? So we can have here, this is the classical way of using Gen AI. You have an assistant calling, talking to your network topology, talking to your alarms, and then giving you the information of what's happening, what we call on-demand observability to understand what's happening in the network. So this is a question of the most occurring alarms, and then this will go into your alarm database that it's, represent the nodes are represented in the graph and giving you the information. That's the classical way of doing. Now the advanced part, which is the value added, is the root cause analysis here, which is happening in second. And we show this also for Docomo. It's 15 seconds for their RAN and transport network. So here, for the purpose of the demo, let me pause a bit. I'm selecting alarm just for the purpose of showing it, but in the real life, the alarms are coming at event pace and depends, each hour, each 10 minutes, each 5 minutes, depending on what is happening in the network. So basically here, as fast as I take the block number 3 of alarms here, as you can see, a couple of seconds, you have the isolation of failure happening. So what's happening behind the scene? All the purple nodes are emitting alarm all at the same time. But the algorithm that we're running there will go and isolate the yellow one as the problem. So you don't need to go for all the alarms to understand or write threshold. This is a graph propagation algorithm behind the scene that will isolate the failure for you and give you the information. And this is also done in the blog that we recently put in place with Docomo. It will go have the agentic AI decide even which algorithm by analyzing your topology structure. So now that you have this failure, you don't do anything. This failure isolation will trigger the other agent to say, now give me the report of what's happening. What's the problem there? So it will go and understand the top 10 that are having the highest score of being the problem, and then giving you the analysis of what happens in the network here. So as you can see, this is the description of the analysis there for the radio access network. So that's one way of doing it. And this can apply to any other type of networks where you can represent the network as a graph, and then you top it with the different type of algorithms. Let me just go to the other case, which is more complex. So this number 4, just to show you how it looks like the network data from the RAN part. So this is, for example, you have the timestamp, you have the node ID, and then you have the different description. And in all network data, you have always some problems in the quality, but this approach is robust to even the data quality part. Here, as you can see, there is some clustering and then some isolation. This is how the cascade of algorithm was doing, decompose and then isolate and then rank the node. And then it is in 15 seconds giving you also the router problem that it's causing the problem to all the others. And then the Gen AI will take this information, those scores, and then go to the Neptune to find the neighborings and then do an analysis for you of what was wrong, which one are affected because they are very close to that, and what type of alarms existed in the, for example, documentation when we described this. So this is those events, for example, in different operators. As I said, they can take from 7 hours plus for complex event because it's a cascade happening across different domain. It can be also cascade happening. Let me stop this a bit. It can be also a cascade happening through the definite layer from the infrastructure to the cloudified network. You need to know where is the problem that is affecting my end user. Is it in the CNF part? Is it in the infrastructure part? I need to isolate the failure to be able to recover.
Honestly, I have, I guess you could call it some form of PTSD of failures in a network where we've literally spent night after night after night trying to solve why we're seeing some form of traffic packet loss or whatever it may be. We would actually implement a change. Wow. We would see the failure. We'd start troubleshooting. We'd run out of our six-hour change window. We'd roll the change back. I'd go to bed and sleep for about 8 hours, wake up in the afternoon and get ready for another night of troubleshooting. Like that's literally what some network engineers do in failure situations.
Exactly. Because they need different tools, right? Different tools, different data. Yeah.
I'm thinking of having spanning tree problems of like, networks blasting each other, and you have to pin down or even unplug different pieces of equipment so that the broadcast storm stops. So yeah, this would definitely help out in finding out what the root cause is. But how does this handle cascading issues? Like if it was something like a spanning tree flood or port band flooding, where you'll see the problem exist in the start, and then because it's caused this flooding, it cascaded out. Can it help there, like stop routing or maybe turn on blocking on some ports or whatever to kind of contain something like that?
So this is for the recovery part, right? And the digital twin will help you to isolate the failure, so understand quickly what is the failure, and can also, if you are using some proactive techniques, you can anticipate. You are seeing weak signal of something that is going to happen. So now for the actuation, once you isolate the problem, you understand what is going to happen, the agentic AI can recommend what to do. And here there is no magic. You need to give the documentation or the rules of what could be the actuation part, and then the Gemini will understand, okay, for that type of failure, for this cascade that you were mentioning, this is the best recommendation that needs to be actuated, and then it will go and execute the recovery in your network. So this is, think of the digital twin as your foundational part, so that the agent can go and do the closed loop, do the execution of the repair that is needed in your network. That's the
We've got a great question from Ken. You beat me to it. Is there a GitHub repo for the code to deploy the experiment with this? Is there a version for non-telco networks? I love that too, non-telco networks, and I'd love to see this in AWS for all of my instances and
Yes.
troubleshooting, everything like that. Yeah.
So we have a couple of examples, not at this level of details, but it is coming in the last blog that I shared. We are going to put in place runbooks with synthetic data to help, the different audits understand how this is running. So these are implementation with customers, with their data. So it's on their environment with their, of course, operational team. But we're going to have some synthetic data and exemplifying how it works. So this is coming soon. And the non-telco is really true. So for the IT, this is applicable for IT infrastructure. This is applicable for IoT also. So this is also, it can go beyond. In any domain where you have dependencies, you can some of these components still useful there.
Yeah. So one of the questions we've got from Venkatesh is, looks like it's a NetBrain tool. Is this built using AWS services like Bedrock? Like I guess they want to know a little bit about what's put together to make this happen.
Yes. So this is built with Bedrock. So Bedrock, we have all the marketplace models there. And then it was built also with Bedrock Agent last year, but now we are in all the new development, we are using Strands Agent. Easier way of building the agent part for the design, but also we have a lot of interaction possible, direct interaction between agent, A2A communication between the agent, and as well as, some swarm or direct graph connection between the different agents. So this is built with Strand Agent, with Bedrock for the models, for the automated reasoning check, for example, to make sure that the model didn't recommend something wrong. We are using automated reasoning checks. For the deep learning, we are using the Graph Storm, which is also by AWS, or you can use from Neptune ML the different graph deep learning. So it's the stack I was showing in one of the slides. It includes the different level of intelligence from the LLM part to the graph deep learning part. Yes, this is built with AWS services. And in the recent blog, if we can share this in the comment part, you will see the different services that we're using, and we had this with our customer Docomo.
Yeah, let's see if I can bring that
Cool.
blog up, and we can maybe. Oh, I can't. Maybe Jamie, if you want to bring it up, my settings are broken.
Let me see what I can do about this.
So the last
Unless you need to reboot to share.
Don't reboot now. So yeah. The last part you want to show in the demo is what does it mean, how it looks like the digital twin. So it's like a moving topology over time, as you said, for all your EC2 instances and all the connection you have, and with links that are showing you if it is red or green, where the problem is happening. And of course, the more you have granularity, the better it is for capturing the different cases that you want to have. So I've seen graphs that are at the 1,000 level. You have like 90K or plus 20K plus nodes, and you have graphs like millions of nodes, 26 plus nodes. So there is no limitation in terms of nodes, but of course we help our customer to model what they need in the graph. It is meant to scale, so you don't need to put everything from the start. Start where You want to have the business case done and successful criteria met, then you model it in the graph, and then you scale it step by step with your scenarios and use cases.
I put the blog in the chat as requested. There's one question I have to ask you, Imen, that I know I will get asked just as soon as I bring this topic up for some of our networking folks. With all of this information gathering, data gathering, do you expect any extra traffic load on the network to get this working? Or is this something that's more like a bolt-on, you can't even tell that it's actually there?
That's a good question. It depends the frequency of collection that you are having from the network element or the network node. So I know for the telco world, it is calibrated to be every 15 minutes or 5 minutes to not overload the network nodes. So it depends here of the network node, how the capacity it is of extraction of the information. But yeah, it has to be adjusted to get the data right. Yeah.
So there's a tuning period where, just like any other type of tool that you're using, you have to make sure that you're tuning it so it's giving you the right information. It's not being part of the problem by adding too much data, all of that.
Yes, and there is also the point of a lot of data it's emitted by the network today. We don't need everything. We also need to have this cycle of filtering, what is really making sense. A lot of data is also correlated together, so you don't need everything because this is reflected on the other data. So that's also the data discovery part that it's done in this kind of project.
You anticipated my next question about the level of filtering of getting rid of the crap data, because that's another thing too that brings up PTSD, is like finding that needle in the haystack through all the data of trying to figure out what is the problem and then realizing that that's not the problem at all.
Yeah.
And then you're making all the changes against it, and then you go find the other needle and then another needle so this definitely gives you a magnifying glass to get to that needle a lot quicker.
Yes. So again, the data is really the foundational part, and the data preparation is very important. There is no magic. Data pipeline, data and AI pipeline, you need to prepare your data. But now we have the LLM. We can master also the semantics between the different, description of the data. We can identify even anomalies in the data governance part and the data cleaning part. This also can help on the data engineering part in general with agentic AI.
So if we're looking at perfect world, right? You've got elements of AI, so you need to have some sort of an AI understanding here. Definitely network understanding, right? Because this is what we're talking about. Do you envision that for the graph database and for the Redshift database, do we need some database expertise here? Or does the solution kind of pretty much build those bottles for you and you don't have to worry about it?
So for building the solution, you need the subject matter expertise in the network and the AI. The AI expertise, that's fundamental. Now, when you are going to put the solution for some adjustment, you use directly our service in AWS, you would need some guidance for the cost effectiveness, like any solution. You need some guidance on that part, but really the most important part is that you understand your network problem right, so that you can frame it right and then select the right AI part of it and the right modeling, where you will store the data engine. So that's the process itself.
Beautiful.
So if we go back to the slide, maybe one of the last. Yeah, the demo is done. So this.
While you're heading back to that slide, I do want to say that my SQL is very bad. I'm terrible. I generally just do a select star and grab everything, and then people complain that the database just broke. And then I say, whoops, now I have everything in Excel I can do something with. But I would say with LLMs now, it's quite amazing. I say, give me a SQL query because I want to find this, this, and this. And lo and behold, there you go, it works. So that kind of stuff has gotten easy for someone like me who doesn't play in that space every single day.
Yeah, but with your expertise, Matt, in the network, you are accessing your SQL database with your network data. You are accessing your topology data with OpenCipher that you don't need to know because this is also managed by the LLM. And then by accessing your alarms, your KPIs, and your topology at the same time through different query languages that you don't need to master, the LLM will master this for you and give you the insights. And once you have this, you can analyze properly because you know your domain, and then you can orient or even recommend, ask the LLM to recommend for you also.
You can understand by having the data presented to you what the actual network problem is, versus how do we even get this data? Oh, it's going to take a week. No, it's actually just a query now to try and ask.
Yeah, you are more focused on the problem instead of analyzing thousands of alarms with thousands of nodes. Then you are shrinking to the 5 that are potential offender. It's quicker naturally, and then you will find the root cause. So I don't know. Yeah, go ahead.
I was going to say, to continue on with both Matt's and my PTSD. Now that we've got a solution in place that analyzes our data, helps us find the root cause of that that issue that may have been cropping up, right? And then we go ahead and do resolution. Now the dreaded RCA comes, right, where we have to fill out like all these 5 whys of what happened. Tell us how this tool can help us out with that.
So in this tool and this demo, it was showing the isolation of failure. So from all these domain or cross layer, this is how you can do it. Now for the root cause analysis itself, you need this kind of documentation nodes. You need to have the description of the connection, so all the topology description. You have to have your SLAs, your constraints, your configuration, and the LLM, because it is now not analyzing thousands of nodes, it's like 3 or 5 that are potential offender. It will go to those databases and make sense. Okay, this is the sequence of alarm that I am having. These are the metrics that I am having, and then it will go to the troubleshooting documentation that are enabled by, for example, telco vendors. And then from there, we'll tell you this is the root cause that is happening. It's in the cabinet. It's a problem of temperature. It will go and find the matching. But if nothing in the documentation, there is no magic. The LM cannot find it. So this is also, again, the data is the fuel. You need to have the troubleshooting description, the possible incident, why it has to be documented so that the LLM can make sense of it.
Nice.
So,
no more chasing down individual folks saying what happened.
Well,
I mean,
I think writing an RCL, root cause analysis, in Amazon when we have a failure, they do happen, is an immense process. It's very, very detailed on everything that went wrong. And I think tools like this could really help do some of the heavy lifting on putting that analysis together.
Yeah.
And so I think, and again, it comes back to the expert knowing their domain and then getting clear, concise data presented to them so that they can write a synopsis of the issue based on the data that's presented to them. So I think you still need experts. The thing that worries me about, and I'm just going to go on a bit of a diatribe for 30 seconds here, with LLMs and AI and making things like this easier, experts are born through almost hardship, right? I mean, if I sit down and study a book, none of it sticks with me. If I have to troubleshoot an issue for 5 hours, that sticks with me, and I know how to work that solution, right? And so I become an expert in that because I'm forced into it. And I almost think that it's extrinsic motivation. There's an issue, you need to fix it, versus intrinsic motivation where, I'm interested in this topic and I'd like to learn it. And so by LLMs and AI making things easier, there's less extrinsic factors at play because everything's taken care of. And so will there be less experts in the future? I don't know, or maybe there'll be experts in different areas and our stuff is irrelevant. That might be another path as well. Who knows? It's interesting to think about that.
I have an opinion on that, and you can test it yourself. If you take your generative AI tool, and if you have the wrong questions or not the right way of asking the question, the LM is going to the wrong direction. But if you are an expert, the most important now is to write the right question to the LM, the right prompt. And if you're an expert, you write it well, so the LLM is guided by that to give you the right answer. So I feel like with the LLM, my opinion, it is like the expertise is even more needed to have the LLM prompted properly, the LLM evaluated properly on whatever it is going to generate. If you are not expert and you ask an AI question to the LLM, you don't know what was generated, why this is the most good approach, or why he selected this model, or why this will work properly, because you don't know. But if you know, you can know this is wrong, this is not what I need. So if you're expert, you guide well, and then you prompt well, and then you put the system properly. That's my opinion.
My fear is that there will be less experts because they don't have to do the hard boots and in the ground, in the mud, digging around to, you know what I mean?
So yeah, if you ask any expert, they can always bring up a point like, Matt, I've known you use the example of bringing down some network access on the eastern side of Australia, and I've done very similar with, a bunch of
with an
flashing
umbrella,
lights.
mind you.
Yeah, with an umbrella, and I've got flashing red lights for traffic in New York City, right? So going through those experiences is what leads you to not repeat those painful things in the future. So if you've got AI going through, right, and solving a lot of these experiences, granted, absolutely, you need the expert in there to guide the AI, right? Because everyone's going to look at that as the source of truth. The expert is more like the captain of the ship, right? Knows all the different jobs and knows what to do and then guides it. But the ultimate question is how do you get more captains?
Maybe AI can fabricate some scenarios to put you through your paces. That's the answer.
Maybe doing something like that, because that's another thing too that I was thinking about as you're going through your examples. It would be really neat where if you had a bunch of these failures show up, right, and you're isolated those failures, and now you've got a fix that you want to do, but you don't want to do it live right away. Could you emulate the scenario with all of that data and with your network and say, okay, if I do this, do I see the problem move?
Yeah. This is definitely one of the use cases. So one of them is root cause analysis. The other one is simulating the changes. So you will say, I'm changing this configuration, this node, but you can, through these, for example, propagation algorithm, understand that with this change, that's what will impact the other node in these kind of parameters. So once you have this dependencies represented, while you move in one of the nodes, you see the impact on the others, and then you can simulate if you want to enforce now or you adjust your configuration. So that's definitely one of the use cases of the digital twin, to simulate the changes and guide the decision of actuation or recovery in the network, or just capacity augmentation. You will verify everything with that. Yeah.
It sounds like we need this on EC2 fleets where you could say, I'm running 1,000 instances right now, and my application is all good, and memory consumption is good, and number of contract entries is fine. Let's drop it down to 750 instances and see what happens. Now, if you did that in production, things fail and then you get fired. But if you can do it on a digital twin, then you can say, well, actually, folks, we don't need to run 1,000 instances. We can run 782. And be just fine. But if you go to 781, things will break. So you can find out where those thresholds could be, in a simulated fashion. That's really cool. I think you had another demo, right, Imen? Should we jump into that? Or?
Oh yeah, I didn't load it in the system. I was planning to on the architecture part, but let's. Should I put it in the?
Oh, if it works, if it's no problem. If not.
Yeah, I wanted to touch base on the architecture side quickly. But
let's do it. Yeah, let's talk about that.
Yeah, thank you. If we can bring it back, the slide 16. Just to answer the question that Jimmy saw on which services that are there. I cannot find the slide here.
I see slide 16 on the. Is it not this one, or is it?
I don't see it on my side here.
Oh, okay. We're actually seeing slide 16, network digital twin as a graph RCA example.
Okay, so if you see it, I know it by heart, so I can go. I don't see it on my. Fine.
So you're being an expert.
Yeah. Exactly. On the bottom part, you have the raw data. So this is the transformation that you need to do through, for example, EMR or Glue. These are kind of PySpark jobs that you need to put in place to transform your data. We are also working with some agentic AI to help on the data engineering to transform the data and accelerate the process. Once it is done, it will land. If you can go to the next slide. I think I can. Yeah, I can go to the next slide actually. So in that front, you will see that it is. You will see that. Yeah, now I see my slide. Great. So in that block, you will see that the data that it's filtered, it is all in these S3 buckets. So it's the topology, the configuration management, and all the other data telemetry. This is a cleaned data. This is now no duplication, no missing data, all the timestamp are correct, etc. And then you can use it. And then in the next one, quickly, you will have all the intelligence started to happen here. So here you are topping this topology, network topology with the graph analytics part from Neptune. You are using SageMaker for having graph deep learning for forecasting and anomalies. And then you are also storing the forecasted value, storing the anomaly. So this is also another knowledge that the LLM will be using. And then you move to the LLM part here. So everything is in Neptune, as I said. And then Neptune is pointing to all the databases with all respect to the different dependencies with the telemetry part. And then you have the agentic part through Bedrock for the models, Strains agent for the agent, and Agent Core for the deployment and operation. And those will be accessing to the different databases where you already cleaned, prepared the data, and making the pipeline evolving over time. And then the agent will make the magic from there. And in the blog that you shared, Matt, previously in the comments, you will see that how we are, if we zoom on the agentic part, so this is, for example, the type of agent that you are going to have for the root cause analysis. This is one of the possible implementation, of course. So the data pipeline coming into Neptune to the telemetry part, or the Lambda where the logic of the root cause analysis of isolation, and then the agent are triggered to do the composition or go and check how my topology looks like, if it is like a mesh network, if it is hierarchy network, and then from there select for me the right algorithm, and then from there give me the scores, analyze the alarms, check the documentation, and return for me what is the root cause or what is the failure happening in the network. So these are the agents that are implemented around the root cause analysis. But it can be a service impact assessment, can be change management for the simulation, as you said. It is the same logic behind this. I think that was the last slide here on the RCA part.
Okay, very cool. Well, we have 5 minutes left. I don't know if you want to share the other demo if it works. If not,
I can share it from my laptop directly, right? We can share this.
Yeah, see if that works. That should work just fine.
That one is also including the let me put it here. Yeah. So that one is using the the video file. Let me share the screen. Share screen, entire screen. So here you don't need an agent, you just need to click. So this is the other demo, and here again it is similar concept, so the same digital twin, but you will see that here it is topped by the forecasting part, so the graph deep learning part. So here I have my topology zoomed into a geographical area. I have my data that are, you see my screen, right?
We can, yeah. It's very small, but I think it's probably okay for other folks.
And you see all the metrics in this dashboard. So what this is like the number of user, the downlink traffic, the uplink, and the throughput and other type of, for example, the number of active users.
So the right-hand side is the MRTG style metrics, and someone was giving me some slack in the chat about mentioning MRTG because no one uses that anymore. But it's a network operation style. Hey, here's all my metrics on traffic, on what have you got?
I still use it for testing.
Yeah.
But the difference is that this is the classical way. Yes, this is those metrics here are okay. This is what we have today. But what is different is, for example, here for each metric you are having the forecasting using some graph deep learning. So here we are using one of the models. It's based on attention type of architecture. So it's attention combined with the graph deep learning to maximize the accuracy of the prediction that we're going to have. So basically your LLM now is even enriched. It is accessing the topology that you see it moving on the bottom. This is your knowledge graph. And this is moving because your temporal metrics are evolving. Your forecasting is also happening. So your LLM is accessing the graph, the forecasted values, and the current metrics. And then the magic from there can happen. So it's 12-minute demo, so I have to just put the right question here so that you can see what you can do. For example, in this question, it is saying, what do the cells, so the cell finishing by T2, neighboring loads looks like now and in the future. So here, if you don't do that, you need to go, to the, you have to go to the inference endpoint to understand what is the forecasted values, then the current values, and then to go understand the neighboring, and then have the consolidated result. Here, you don't need to do that, which is just the question.
That's such a powerful query, because you're essentially saying, hey, I've got this network router, tell me what my bottlenecks are.
Exactly.
Yeah. And then forecast for the future.
Such a vague thing. And sorry, go ahead.
Yeah, exactly. So because it is accessing this knowledge, it will give you, this is my current, router, for example, metrics. Those are the one happening in the next hour. And this is the analysis because it knows which router connected to which one and which network interface in between. So this is the logic of digital twin. You give the power to your LLM to access your data, represented in the right format and evolving because it represents your network exactly as it is, and then it gives you all the information. And you can see this is, very quick and accessing, 1,000 of metrics that you are having from different sources. If I go to another one, which is like on the query side. So this is, for example, you don't need yourself to write the query. You will ask, for example, list for me the closest cell in terms of distance, geographical distance. And here it is, if you don't know the open cipher, the grammar you don't need. This will happen directly with the LLM that will go and write for you the query for the graph databases and give you the information of those are the 3 closest cell, and then it will calculate the distance, etc. You don't need even to add.
Like how I was mentioning earlier.
Yeah, there you go, Matt.
It was crappy. We don't need to do that anymore. This is great.
and you go directly to do many analysis. And there is another one which I like here. It's about the, for example, you're going to have, this is around the simulation part. I think you asked about this question. I can't remember where's the question here. It's coming up. Yeah, for example, here we have sport event happening. 1K users are expected. So how to adjust the G-Node configuration? Then here is also, again, the model understand the current status, the forecasted values, the metric of 1K user, the neighboring around and accessing the configuration. It will go and give you the simulation of what will happen and what will be the configuration part. So this is the simulation.
Well, Imen, we are out of time, actually. I got super interested in this last demo because it's so cool, but that's all we got time for today. We're actually right on the clock now. Thank you so much. It's been so interesting.
Yeah, we can definitely,
Yeah. Okay. Well, we can probably follow up again, but thanks everyone for joining us today. We've had Imen on talking about agentic AI and network observability and root cause analysis. Thanks, Jamie, for joining us too. We'll see you folks next week.
See you next week.